Hello again, everyone. It is a great pleasure to introduce Asaf. Asaf recently started his PhD in physics in Columbia University, and he will soon start to work in one of the most prominent AMO labs in the world. Together with Asaf, we studied Bose Einstein condensates. And again, I don't know how much I was able to help Asaf, but I definitely learned a lot from him. And again, as you will see soon, he did a great job studying the subject. And the stage is yours, Asaf.
Thank you again. Um, I hope this is okay. So hello everyone. I am Asaf. As again introduced, I am a PhD student at Columbia University, and I will talk about the essentials of Bose-Einstein condensation today. So my outline is like this. I will talk about it differently than the other presentations. I will talk about the strategy about how should we understand the big picture of these many-body systems and introduce a Bose-Einstein condensate. I'll define it, and I'll do a simple case study with non-interacting bosons, and then do the main part of our presentation, the weakly interacting bosons, then introduced the Gross-Pitaevskii equation that describes these Bose-Einstein condensates, and finish with an outlook. So in general, what my take on how to do physics is that we usually consider a system. This could be a quantum or classical or even a biological system. We write down the physical equations governing the system, and these are usually either the Hamiltonian or the Lagrangians. And these are important mathematical tools improved back early in the history of physics that helps us even to this day. And we derive equations of motion from these physical equations and deduce physical properties of the system. So what's a Bose-Einstein condensate? Bose-Einstein condensate is essentially a state of matter. But when we say a state of matter, we should think of prominent specific statistics. This could be a solid statistics, liquid statistics, or gaseous statistics, or plasma statistics. But in our case, it's Bose-Einstein statistics, just like the photons. And this state occurs in the quantum scale. And when we say quantum scale, we usually mean that the objects that have de Broglie wavelengths comparable to their scale, which maybe you remember from high school. And up to this day, there are lots of Bose-Einstein condensates created from different kinds of atoms: sodium, rubidium, lithium, cesium, and many more. Even now we have molecule Bose-Einstein condensates, and here you see a time evolution of a Bose-Einstein condensate, formation of a Bose-Einstein condensate from rubidium, from sodium, and this was actually the first Bose-Einstein condensate we could create back in 2001. So one important concept that we need to understand is the distinguishability. So when in everyday life, when you have blue marbles or turquoise truncate octahedrons, you can usually differentiate between these objects, even though they have the same color or the same shape. You can label them with your eye and track their motion and where do they go. So, but in a quantum case, we usually have really small objects in a quantum scale, and then it becomes hard to label things, and we essentially cannot label things. So we cannot eye track which atom goes where or which molecule does what. So for example, if you have two particles at time t, and when you look at them at a later time, you won't know if they change places or stay in the same place. One important thing that we need to create a Bose-Einstein condensate, this distinguishability feature of our system. So that's why we usually use bosons, and for fermions, we cannot create a Bose-Einstein condensate because they don't obey the statistics required. So what are bosons then? So formally, bosons can be defined as complex fields having integer spin particles, but the most important feature of them is when you put a lot of bosons and a lot of fermions to the same space, fermions always tend to build up and form a sea. You can remember this as the Pauli exclusion principle from your high school. They cannot have the same state, while bosons can. So in essence, what I imagine when I talk about Bose-Einstein condensate is that a gaseous marbles on top of each other in a marble stack. And if you could write that state in terms of our usual quantum notation, this would be having this no particle state. This cat here would notate having no particles in our system, and this n would notate having n particles in our system. But as you can see by looking at this notation, we cannot understand other properties, but only the number of the system, because we cannot distinguish between all other bosons in our system. So our most basic case is a no interacting boson case, no interaction case. Or in this case, this is usually an ideal case. We usually don't have these systems in the lab, but we don't have any interaction energy. Bosons, no interaction means bosons do not sense each other in that term, and they behave as if they are a single particle. So since they cannot feel or see each other, they only interact with the environment, and if there's no environment, they only have kinetic energy. So, for example, when we want to describe the system in terms of Hamiltonian, we write this as we only have the kinetic energy term here, notated by epsilon k, and how much particles we have in that energy level. So, for example, in this summation, you may have different bosons, different particles at different k states, but this term here would give us our total energy term. And in sake of disclosure, to make this transition here, this is only the momentum term or the kinetic energy term that particles have in quantum scale. So we can actually, even though this system is extremely simple, we can still deduce important physical properties. For example, we can deduce by looking at the temperature of the system, we can deduce how dense they can be, or what is the critical temperature to observe this transition from any gaseous state to the Bose-Einstein state, just like the picture you saw of formation of Bose-Einstein condensates with sodiums. So next step in our system, we'll be considering interactions. And since we don't alter our understanding very deeply, we usually start considering our weak interactions. And to model interactions, we have certain equations that we can write down. So while we're writing the Hamiltonian itself, we usually have scalar interactions. The terms that drive the interaction term may not be scalar, but we have to use scalar potential to write Hamiltonians. This could be Coulomb interaction, just like the electric field of a charged particle, or dipolar interaction, just like the magnetic field of a magnet that you have. And in that sense, they encode some sense of feeling towards each other. And since we need to write these interactions, so each interaction increases our energy, so we need to write every combination of possible interactions. And to write this down on our Hamiltonian, we usually consider ith particle interaction with the j particle, and the j particle interaction with the ith particle. So as you can see, this is double counting, so that's why we have these 1/2 factor in our Hamiltonian. So the first important mechanism to write down as the interaction energy is a scattering process in this gas of boson we have. And we usually consider the low energy collisions because we usually consider the lowest energy events to describe some property of a system. And the best or the easiest approximation we can make is this ultra local approximation. This essentially means that as long as particles are different positions, they don't feel each other, but as long as they occupy the same position in space, they have this energy term or the potential energy term in our Hamiltonian. So to consider the scattering process, the method we use called is partial wave analysis. And this essentially means that we write down the motion of the incoming particle in a certain basis that will match the energy regions that have this particle have around. And when we do the calculations and match the boundary conditions and everything, we get this simplest term out to our Hamiltonian that we can add. And that depends on essentially the scattering length, the length that particle field will be sensed by the other one, and the mass of the atoms we have in our system. So after we write down the particle or the scattering energy term in our Hamiltonian, we have to study or work out the Hamiltonian we have. And to do this, the best method we have is writing the Hamiltonian in the second quantization notation. So this means that since we have this indistinguishable particles, we essentially cannot track which particles go where, because they are exactly the same. They don't have anything different. So what do we do is that which kinds of motion or which kind of modes are present in the system. The second quantization helps us with that. And when we write this Hamiltonian like this in second quantization, the first term is, again, the kinetic energy term each particle have, or the energy or our system have for each K. And we have this complicated term here. For the sake of understanding, you can imagine each K vector here, the momentum vector that we have in each three-dimensional axes. And when we write down the calculations and make derivations, we have this energy term. And as you can see, the energy term now is updated by this little term here. And we usually tend to keep this term small because we are in the weakly interacting regime. And we can, for example, calculate how the vibrations in this atomic gas propagates, or we can calculate the compressibility or many other thermodynamic properties of this gas of bosons we have. So if you are not familiar, so probably you're not familiar with the second quantization concept, but just a fun fact, when we say first quantization, we mean which energy levels are allowed. This was the first revelation we had in quantum mechanics, the quantized energy levels of hydrogen atom, or quantized energy levels of a photon. But now we have the second quantization, and this means, as I mentioned, which modes are we allowed to have, because we cannot have a continuum of modes dictated by the system. So when we write this down, so when we write this Hamiltonian in the second quantization and make the appropriate approximations, we obtain the Gross-Pitaevskii equation. So in its essence, Gross-Pitaevskii equation is not a true equation in that sense. It doesn't account for actual laws, just unlike Schrödinger equation does, or the Newton's second equation does. So this is a model equation that we created by ourselves to model mostly the weak interaction. And this is, maybe there are some physicists around you. So this is written in the ground canonical ensemble, which means that we have this gas of atoms. And when we want to add particles to our system, this requires some energy because they will be interacting with each other. So writing the Hamiltonian in ground canonical ensemble helps us understand what happens when the system can exchange energy and particles with its surroundings, because this happens all the time. Even in the best labs, we always have these outliers out of our gases that can enter the condensate, leave the condensate, or just cause energy transaction between these two. So when we write this Hamiltonian, this Hamiltonian, or this equation actually offers rich physics with really, really interesting physics. We already observed really interesting phenomena. Even with this simple equation, we observed the superfluid state in which a gas of atoms do not have any viscosity, so they can flow without any resistance, or supersolid state, which essentially a solid system that can flow without any friction. And there are many more phases that we still try to understand. And if we want to go even more to make our life harder in the lab, we usually tend to make easier approximations. And when we get a good lab and when we get a good gas in our experiment, this means that we can get our atoms to the really, really, really low translational energy level, so they don't move a lot. We can just throw this kinetic energy term that we have, which is called Thomas Fermi approximation, and find really we can find states with really low energies that has no kinetic energy but the potential energy that we apply and the interaction term that they have. So at the end of the day, there are really different interesting experiments that is investigating the problems around these BECs. Even though we can create BECs, there are lots of things that we still don't understand. So for example, when you write down the equations, you'll see that BEC cannot rotate if there is no zero density point in somewhere in the BEC. So for example, you see a formation of vortex lattices here. This means that you can, when you try to rotate your BEC by probing it with a laser, it forms a hole here, a zero density point. And when you go along with the rotation, you see other holes. So, and at the end of and as you go along, you'll see that these vortex lattices that BEC rotates around in really, really, really many numbers and in a very ordered system. So it was really interesting that these vortex lattices that we have, these nearly perfect ordered systems. The other interesting way to go is actually happening in the group I'm working with. So when as you remember, in this presentation, we modeled interactions really simply, and they were isotropic and they were really weak, but there are different kinds of interactions we have. For example, an isotropic interaction, it really depends on where two particles are in our system, because the energy term depends on this theta. And because of these type of interactions, creating BECs out of these systems is actually really hard. And the Will group at Columbia was able to create a molecule of BECs that have these anisotropic interactions within the past year, I guess. And there are some interesting matter facts. For example, we have this topological edge mode. And what you see in these figures is that we have these two regions in space. And here, the potential, there is no energy applied to the system. And there is some elevation to the gas in the system. Even though I would expect gas to propagate to the region that have no potential, when you realize the experiment, you see that they actually tend to stay in the limit of the no potential region and the potential region. And one other interesting experiment is investigating the Fermi-Hubbard model to understand superconductivity. But in the Fermi-Hubbard model, it's usually studied in solids, and you need to have a unit filling of these patterns that you have in your crystal. And Becker group at Princeton was able to create a system, for example, understand the single field traps and the double field traps. And this was a really improvement in the field to be able to investigate Fermi-Hubbard model. So this would be my presentation. Thank you for listening. And if you have any questions or any queries, please send me an email. And I hope it was a real interesting presentation for you. And yeah, thank you.